Hello community! Today we talk about some crazy stuff, how agents use your Monte Carlo Tree Search to improve the system performance. So yesterday we looked here at Salesforce, Microsoft and Anthropic for their brand new AI agents and their agentic business application. And today we're going to look at the latest AI research here from University of California, UC Berkeley, Stanford University, and some other beautiful institutions. And if I look here at my paper today that I will explore here, you see here autonomous agents here, multi-agent collaboration network for software development, LLMs empowered here for the web agents, navigation for multi-agent robotic systems, creativity multi-agent learning, deploying robot swarm behavior and agent-based emulation. Everything is now about agent in the research community, and you might ask a simple question: why are they not focusing on improving our LLMs or our vision language models? Well, you could argue, well, they do now. We have here Anthropic just some days ago, they presented us a new Claude 3.5 Sonnet, an updated version. Now, if you look at the old Claude 3.5 Sonnet, you see the improvement was 5%, the improvement was 3%, the improvement was 1.7%, and some, like mathematics here, you see we go from 9% performance to 16% performance, and you might say, okay, so from 5 to 1.7% performance, this is okay. But I would like to show you something else. Look at this in a different way. You see that different tasks here, different specific tasks have different model performance. So this new model has been trained for a very particular set of specific tasks, like a benchmark data set. And this new model has been trained here in a very specific data environment that maybe is published, maybe it is not published at all, with some specific data formats on a specific training implementation for the model, published or not published. And then the pipeline from the first raw data to the final task-specific trained model, this is what we call normally a machine learning pipeline. Now, the beautiful thing is that here Anthropic states here the new Claude 3.5 Sonnet offers the advancement, 1.7%, at the same price and at the same speed as its predecessor. Remember, we are here in a business environment and you have to pay for this. Great. Let's look at this a little bit more abstract, no? We have biochemical task in science, or we have a traffic management task, you want to employ AI, or you are working in a hospital, you have medical tasks. So how you start? You have your very specific raw data. This might be images from different medical machines or whatever, and you have a very specific task. And you have only a very specific task because you want to have an answer to your particular question. So how do we start? Now, medicine, you have raw data. You prepare this raw data in a specific format. You have to take care about the noise. If you have an X-ray machine, for example, you have specific routines to optimize here the data representation. And then you bring your data in a specific format where this vision language model knows exactly how to deal with this particular data format, since this is the data format that this VLM has been trained on. So it is absolutely familiar and it performs best on a particular data format. Now, you take the latest vision language model, and then you choose, well, maybe I just take here the 1 billion free parameter model, and then you say, I perform maybe a quantization, I go down to 1.58 bit, so really the smallest model possible here, and then I have it here, and then I have here my AI intelligence, a 1 billion free trainable parameter model, quantized down to 1.58 bits. And then you say, now I'm ready, but now I do some huge function calling. I have my external knowledge, I have my databases, I have my medical graph knowledge. I now bring everything into this, and then I do a self-reflective chain of thought, causal reasoning with verification function that are specific to my medical task. and you're saying, hey, yeah, this is it. No, this must be the perfect pipeline for this specific task. So we started here with very specific raw data from your medical machine, and you have a specific task at the end that you want an answer to. Another question is this the best machine learning pipeline or not? And I guess you understand at this point now where I would like to argue about today. Not just to argue, but show you where is the research happening today. The Wisdom, University of California, Berkeley, Hong Kong University, University of California, San Diego, South China University, Stanford University, Chinese University, and Montreal University. And they published the October 22nd, 2024, a Tree-Search Enhanced LLM Agent structure for automated machine learning. So this is now interesting because we throw in everything that we know. No? We have our LLM, our beautiful, highly trained LLM, trained on 10,000 GPUs. Then we have built our agents out of this LLM with memory and causal reasoning and particular prompt engineering structure and whatever went into our agent definition. And then we add now a tree search. And you might ask, why is this necessary? Let's talk about this. And we have one goal why we do this. And this is why we want to have an automation of the complete machine learning process, of the complete pipeline to enhance the performance of our system. We want a better performance. So what do we focus on? The LLM, the agent construction, a tree search enhanced LLM agent for a particular task, the complete pipeline. Stanford, UC Berkeley and all, they try to answer this now. And you see, this is what we are researching today. Machine learning is more than just a simple large language model or a vision language model or a robotic model. It is about a thoughtful integration of data, the algorithm you will use, and the processes here to solve specific problems effectively. And by optimizing here the complete machine learning pipeline, you simply achieve a better performance. You have flexibility and you have the compliance, but main point, you simply outperform your competitors. Now, each component of this classical, let's go with the classical idea of a machine learning pipeline, contributes here uniquely to the final outcome because you have the issue of data quality. High quality data is absolutely essential. You want to have here the features that you want to extract, where the intelligence of the AI, of the LLM, will attach to and try to find patterns. So if your feature extraction is not at 100%, the system will simply not learn the correct relationships and will not have here the accuracy that you're looking for. Model appropriateness. The best model for one task might not be at all the best model for a very similar task, but with another data format. So selecting here and tuning here the right model is simply crucial. Even the most accurate model you can buy is ineffective if you cannot be deployed here efficiently. And it fails to integrate with the existing data formats, with the existing data pipeline structures. And you want that this process is a continuous improving process with monitoring and updating as needed, given the complexity of your task. And let me give you an example. Simple. What is the simplest thing you can think of? Automating the categorization and routing here of customer support tickets. So we have simple steps, no? This is what we know. We have 100,000 GitHub repos on this. We do have the code. So what we have a data preprocessing, no? Cleaning the text data by removing different tags, correcting here the typos, normalizing the text. Then we have what we call feature engineering, no? Converting the text to numerical representation using different embeddings, whatever you can choose from. And then we have the model selection. And you have here the non-AI models, maybe they work just fine. Or you go here with the deep learning AI models. And then you have all whatever there is fine-tuning, instruction fine-tuning, different format, different ordering, different positive and negative formulated instruction fine-tuning sequences, whatever you can imagine. And finally, the outcome here is a customized pipeline. It's simply improving here the accuracy of the ticket categorization, leading to a faster response time for your customer satisfaction. Yeah? But look at this. So the idea is now simple. Hey, we take this, what we have, no? Data preprocessing, feature engineering, model selection. And then we know that we have so many ways to code this. I don't know how many GitHub repos we have on data processing, maybe 100,000. So let's just think about the 4 most performant models, the most performant GitHub repos for data preprocessing for your specific textual data, visual data, video data, audio data, whatever you have. We do the same with feature engineering. You want here to really extract the features that are important for you, for your model, X-ray images. We have, 10,000 different possibilities to do this. Let's take the best 4. The model selection. Yeah, you get the idea. So, I can build with all of this that we know that the models know on the code, LLMs and everything. I can build a real huge complex mathematical space for all of this solution and the combination of all of this solution. And we have best practice, we have really famous GitHub repos where 99% of the coders just follow here the given path that one person found to be effective. But if I want to improve my performance, if I want to outperform my competitors, but how to search this huge solution space for the optimal solution for my very specific task, for a very specific task configuration, simply what we call a pipeline. And now this is the research where Stanford University, University of California, Berkeley, all comes in. Now they are focusing on this configuration. And classical, we have a tree structure, no? We have a starting node, a root node, and then we have 2 different nodes, the so-called, I don't know if you want, they are subnode or leaves or whatever you call them in a tree structure. And you continue with this process and you generate here n steps. Now, if we apply this idea, the simplest idea of a tree structure, let's do this here for our example, yeah? And then we apply this here. The first level is data preprocessing. I showed you the blue box. The level 2 is feature engineering. I showed you the second blue box. And then, you're not going to believe it, the third blue box, the level 3, is now model training. So let's have a look at this in a little bit more detail. The beauty of this is here, we build here certain paths through our tree structure where we end up with an end leaf here, where we can say, okay, I have now a complete path. I can calculate the performance of this particular model doing this particular code implementations. And you know what we're going to do now. Now we're going to do some random simulations here. We'll do a Monte Carlo methodology we apply here to the tree search to guide here the exploration of the complex and huge search space. This is one of the best methodologies we have. And you know how it functions. Instead here of relying on predefined heuristic function to evaluate now the nodes, our Monte Carlo Tree Search uses some random simulation to estimate the value. This is especially useful in domains where defining a good heuristic is very difficult or maybe even impossible. And then we have this beautiful balance between exploration, trying out new options, and exploitation, focusing on already working promising solution and trying to optimize those solutions using here statistical measures like an upper confidence bound, UCB and UCT, I'll show you in a second. And then this system gradually improves its understanding of the search space through repeated simulation until suddenly the system converges here to better solution. Let's have a look at this. Yeah, if you want to have a literature about upper confidence bound and upper confidence bounds for trees, this is a paper I would recommend, Hungarian Academy of Science from 2006. But what we follow is an easy logic. Now we have a root node, a level 1 node, level 2 node, level 3 nodes, and you get the idea. And as I told you, level 1, different data preprocessing choices. Level 2 node, feature engineering methodologies. Put in 100 different. Or level 3 node, diverse model training options. Great. Let's have a look at this. let's zoom in here to the first third here of this image, and here we have it. Now, data preprocessing, feature engineering, model training. And now we have here on the level 1, we have a node P1, remove the stop words from the text. Very simple example. Next level, node F1A, convert text to TF-IDF features. Or model training, use a logistic regression classifier or support vector machine classifier with a linear kernel. Or generate n-gram features, bigrams, trigrams, whatever you see. So when you go here from one level to the next level, and you create here a sub-leaf or a daughter leaf or whatever you call it, it doesn't matter. You just go down here the rabbit hole and you have more and more precise defined methodologies where we have simply a GitHub code available. So the system, the next step, is able to pick this up and just code it and run it for us. And we have a Monte Carlo Tree Search simulation where we have now an evaluation of all the different ideas. And you see, if we do this here for the first part, then we go now from the node P1, let's say we only have 3 levels, we go down to the node P2. So instead of the idea of removing stop words from the text for a data preprocessing, we have now another idea. Node P2, apply lemmatization to the text. Or node P3, correct spelling errors in the text. And then for each node, you see, we go down level 2, level 3, and we construct here our sub-nodes, our sub-leaves, and we can do all the calculations in the world for this. Now, the research here by Stanford and Berkeley and whoever, they used here this SELA methodology where the LLM, and let's make clear, the intelligence is still here on the LLM. So if the LLM is not performing, this system will collapse. You need an LLM that is able of handling a complexity for your task. So, and now let's say we have this beautiful, huge LLM that is able to understand everything that we want from it. So what we have different type of model, different type of data preprocessing techniques, different feature engineering methodology, different hyperparameter optimization strategy, different evaluation metrics, and our LLM must have been trained on, 10 million GitHub repos, plus text to understand here how are different preprocessing techniques impacting the performance. What are different feature engineering methods? Because the LLM will come up with these options. Plus, our third step is to code whatever was built. Because we want to go through each tree branch up to the end leaf and calculate the performance and then have the backpropagation on the tree to optimize the structure. So this LLM must be able to write a valid and effective code out whatever we designed, found here in our evaluation structure. Now, you don't have to go with one LLM. You can use one LLM for the planning, and then you use a code LLM. Maybe you go with 3.5 Sonnet for the coding, or you go with Cursor for the coding. You have so many options. And then the LLM must learn that different machine learning concepts relate to each other and which methods are now suitable for specific types of data or task, and how different choices can impact the performance of the complete machine learning pipeline. So you see, we said goodbye to only looking at the performance of a large language model or a VLM. We now optimize the complete system performance. And let's say we do not know the perfect solution. We just know a solution that 2-3 people found, 1 year ago, and now 99% of all the coders use exactly this code segment. But maybe this is not the best available methodology to solve your particular task. Or maybe just a little bit different task has a complete different structure that has a much better performance. So we open up here the complete, if you want, spectrum of find the best system architecture, the best pipeline, the best machine learning pipeline. If you have your raw data, you have a specific task. You're looking for a specific answer. and the configuration of the pipeline is not known. So what we have now, and this is the main idea, you have all the strength of a large language model here, plus a structured search and refinement process here in our, if you want, solution space, where we can build here a huge amount here of possible solution and alteration and combinations of how you put together here a machine learning pipeline for a particular problem, given here your particular data structure. And the authors argue, yeah, this is what human experts do, no? They play around, they try different methodologies. So this is not the content. They say, okay, we have a 3-step process. We have the insight proposer, as I showed you here, the data preprocessing step, the feature engineering step, or the model selection step. For your task, it might be a complete different combination. You might need something completely different, and the LLM must be able to understand your task and have been trained in the pre-training data how to handle your specific task. And each and every task is different, finally. So then, second step is here, the navigator, the search model. And now we employ here on this huge space of all the possibilities here, Monte Carlo Tree Search as an exploration engine. And this engine travels here. It's traversing here the vast search space of all the potential configuration of our pipelines. And we do this in a simple tree structure, and we can evaluate this. And how do we evaluate it? We code it. So the LLM agent serves now as a hands-on engineer, and it translates here our pipeline configuration into executable code segments. And we run this code, we get a performance back, and then backpropagation, and we optimize here our Monte Carlo Tree Search algorithm. You see, simple ideas brought together, and this is all you need to find here a better solution. Now, the authors of SELA here, the last one, showed us here, they compared it now with different methodologies. Autolearn from 2020, AutoScaleRearn from 2020, the data interpreter methodology from 2024, or 8 from 2024. And you see here all the different features, and they say, hey, what we achieved here is this beautiful stepwise Monte Carlo Tree Search methodology, plus using here the intelligence of the LLM. And how this is working is a, well, easy 3-step. We have here the problem description and the raw data that we have. We put this into a prompt to the LLM. The LLM has been specifically trained for this and is now able to generate our search space. It understands for solving the problem given, it needs to do step A, B, C, D. Let's say A is data preprocessing, feature engineering, model training, hyperparameter tuning, optimization, whatever. And then, second step, if we have generated this huge search space, we find now here a methodology to search, to really explore this huge search space with a Monte Carlo Tree Search algorithm. If you have any other methodology, please use it here. And then we evaluate here each path through each leaf and end leaf and root. And then we do here the LLM auto codes now this in code solution. We run this now for each particular path here through our tree, and we get a result. We have the backpropagation and the optimization here of our tree. So we try and error, try and error, and try and error methodologies are applied until a specific stopping condition is reached. After 100 iterations stop, or if, I don't know, some parameter, some benchmark parameter is below a specific threshold. So you see a rather simple idea. What is the performance? And they give you here the results in chapter 4.2. And they say, hey, we use here normalized score. So they say our performance here of our SELA is here this for all the different tasks you have here for all the different data sets. This is here our normalized to 1 performance of SELA. And you see everything that is below 1, this is this huge space here, is not as good as our methodology. And sometimes you see here in this particular task, yeah, okay, they are better. But if you have a look overall, you see almost all of the models for all of the different data sets and different tasks are not as good as here. The normalized SELA performance, normalized to 1.0. So, looks interesting, but careful. This is really computational expensive. This is a really huge search algorithm here. And the more complex your task is, the more maybe an exponential growth of your solution space is possible. And then you have to pay, or you have to have the time for the different routines to run all of this code and to come back with perfect solutions. So, not a new idea at all. This is a logical evolution steps. Some research was already performed really similar to this idea on different parameters, on different configuration. But just wanted to show you, this is where AI research is happening today. This is where Stanford or Berkeley are publishing now their results. They want here a system performance. They do not focus here on component performance, but it is all about performance, about the system. So, for my green grasshoppers, bringing it all together, what are the simple steps here of our new SELA workflow? Okay, we have to initialize the whole complex. We have an input problem description and the dataset information of the raw data that we have here. This is our basis. And then the LLM generates here insights for each pipeline stage, forming here the search space available to us. Then we use here this particular Monte Carlo Tree Search methodology, or you use an advanced methodology if you want. We have the selection process, the expansion process, the simulation process, and then the optimization with the backpropagation. Plus, then we have the iterative refinement if we have this. The process repeats here for a predefined number of iteration or until we have a convergence or a specific threshold. And then this pipeline configuration with the highest performance, remember, going back through all the different nodes, all the different leaves, we found one path that has the best performance. The best performance metric is now here available, and we select exactly this pipeline configuration. And then our LLM agent, our code LLM, or maybe you as a human, you sit down and you code exactly this structure of the three elements here for the deployment of the system. Okay, you see, a simple idea. Study itself is a little bit more complex if you want to read it yourself, but I hope I've given you here the main idea, what they achieved, what is now currently AI research, and it would be great to see you in my next video.